So in the previous video, we did some dynamic surveys, which gave us different questions dynamically. We also created a results page that saved information in JSON. But sometimes you want to save something a little bit more complex. You can think of saving something in JSON like having it a little notebook, saving some information. But sometimes you want to save a lot more information, and saving it in a notebook is not really the most efficient way of going about it. What you want to do is save it in a database. So what is a database? Let's talk about it.
Companies both large and small rely heavily on databases to power their applications. For instance, Shutterfly, the popular photo publishing site, uses something called a non-relational database to help manage their image data. But at the same time, they also use a relational database to help organize their customers' billing information. Without those databases, Shutterfly wouldn't be able to function. Now, if you didn't understand the database types I just mentioned, that's totally okay, because that's what we're covering here in this video. Simply put, databases store a variety of data, such as usernames, email addresses, hopefully encrypted passwords, and virtually any other type of data that you can imagine. Now, there's a variety of databases out there. The ones we'll be covering specifically are flat files, non-relational databases, and relational databases. Flat files are databases that store data in plain files. Each data record is separated by delimiters, such as commas or tabs, and the benefit of flat files is their simplicity. But when building an application, you often need more flexibility, which is where a database management system comes in. Database management systems are software that handle the storage, retrieval, and updating of data. The common two types are non-relational databases, or NoSQL, and relational databases, which use SQL. And if you don't know, SQL stands for Structured Query Language, which is a language that makes it possible to easily manage the requested data. So when would you want to use a NoSQL database? Well, as we talked about in the intro, Shutterfly uses NoSQL to store image metadata. This is a good use case because the image data doesn't necessarily require a lot of structure and can be stored as a key value pair. Now, some examples of NoSQL database management systems that are available are MongoDB, Couchbase, and Amazon DynamoDB. NoSQL databases are fantastic for certain use cases, but then other instances will require that you use a relational database. That's why in our example at the beginning, Shutterfly uses both types of databases. In the relational database, they might have 3 separate tables. One for the customer's information, 2 for the billing information, and the 3rd for images that a user has uploaded. With a relational database in one SQL command, you're able to pull all that information across all of those tables, which would not be as easily accomplished with a non-relational database. Some examples of relational database management systems are PostgreSQL, MS SQL, and MySQL. So overall, we covered what databases are, some of the various types of databases, and now the next thing to do is to actually learn how to work with them.
Okay, that's what a database is. I also want to talk about how we interact with databases using something called SQL or SQL.
Structured Query Language, SQL or SQL for short, is the gold standard language for communicating with relational database management systems. You've likely heard of databases like MySQL, Postgres, Microsoft SQL Server, and Oracle, all of which are based on SQL with their own little variations. It was initially developed in the early 70s to mutate and retrieve data from IBM's System R database. By 1986, it was standardized into the syntax that remains extremely popular in technical applications today. A relational database organizes data into tables, kind of like an Excel spreadsheet, where columns contain attributes or types of data, while each row represents an individual record or data point with its own unique ID known as a primary key. We can establish relationships between data points by taking the unique ID from one row and storing it on a different row in a different table in a special column known as a foreign key. In the teams table, the team ID is the primary key, but in the players table, it's the foreign key. And what that data structure tells us is that a player belongs to one team, while a team can have many players. What we've done here is structured our data in its smallest normal form to eliminate duplication and redundancy. Now, the role of SQL is not only to read, create, update, and delete data, but also to join data together based on the relationships embedded within it. The syntax is comprised of several key parts. If we zoom all the way out, we have a statement, or a piece of code that does something, like reads or writes to the database. Within a statement, we have a variety of keywords that can manipulate the database. Select can be used to make a query for the columns that you want from a table. The column and table names are known as identifiers, but we may not want every row in the table, so we filter the results with the where keyword to only include records that meet a certain condition. It's like looping over every row in the table and only returning rows in the query where the predicate evaluates to true. Then, we might use the join keyword to connect data from an entirely different table, by matching the primary key on this table to the foreign key on another table. What we've created is a collection of clauses that make up a full SQL statement. We can now go and execute this code on the hundreds of different databases that support SQL.
Okay, so that's SQL. But typically when you write web applications in the modern era, we don't directly use SQL to communicate with databases, just because databases have their own structure for data, and that's not usually the way that we structure data inside of a program. So we use something called a ORM to communicate with databases to make it a little bit easier.
Why use ORMs? As developers working on the back end, we have a problem. In the programming world, the default way of modeling reality is by using object-oriented programming. However, the default standard for modeling data in a database is by using tables. These two, objects and table rows, aren't directly compatible in terms of our mental model. There's kind of like a gap. And this is where ORMs like Prisma and Doctrine and Active Record or Laravel's Eloquent come into play. They help bridge the gap between two mental models, between tabular data and object-oriented programming. ORMs map data between objects and databases, hence the name. ORM means Object-Relational Mapping. They make life so much easier. However, that isn't without drawbacks. We'll get to that later. First, what are ORM's main advantages? First, ORMs allow you to interact with databases using a syntax you're familiar with. It makes developing a lot easier. This conversion abstracts away the subtleties of working with a database, and by doing so, it provides the second advantage. It removes a whole load of boilerplate code. And that brings us to the third advantage. Less code means less maintenance and fewer bugs. It means code that is easier to read. It means a better developer experience all round. Less code makes life easier for everyone. Fourthly, in some cases, such as for Prisma, the ORM can allow you to have a shared interface that abstracts away the details of the underlying database. You tell it what you want to get, and it worries about how to get it. However, that level of abstraction, of indirection, comes at a cost. I count 5 points to watch out for. First of all, ORMs can introduce a performance overhead because they need to translate between the database and the programming language. Second, ORM can hide important details about the underlying database, which can lead to unexpected behavior or performance issues. If you don't know exactly what the ORM is doing, it's difficult to optimize how you use it. Third, ORMs are often less flexible than accessing the underlying database. This can also mean that you are less able to optimize how you query the database because you don't have the flexibility to specify precisely what you need the generated query to look like. Fourth, ORMs introduce maintenance overhead. They need to be updated regularly to keep track of new features in the underlying database technology. And fifth, ORMs add complexity to an application. They require an in-depth understanding of the ORM's behavior and limitations. This can actually make it more difficult to debug and optimize. It's essential to carefully consider the specific requirements of a project before deciding to use an ORM, and to be mindful of the potential limitations and trade-offs. Now, what does this mean? Should we shy away from ORMs because of this? No. Despite all these pitfalls, ORMs are still a valuable tool for many applications, and they can greatly simplify the development process. In most cases, the ORM is your friend. However, it's important to understand what the drawbacks are. To get the most out of your ORM, you need to understand what is going on behind the scenes, what behaviors it's introducing, what queries it is generating. Understanding how your ORM works is vital for the long-term success of what you're developing.
Finally, I want to talk about how we interact with data in a web application. We use the method called CRUD.
At the heart of a dynamic application is a database. Whether the application is an e-commerce or social network, or even a to-do app on your phone, the data needs to change over time. For example, if you run an e-commerce site, you'd want to search the products, update stock counts, create new orders or new products in your database, and remove all discontinued products. The site is dynamic because the state changes all the time. CRUD is an acronym that refers to the 4 main operations that you'd want to perform on data in a database. First, you want to be able to create or add data to a database. Second, you want to read the data. Reading would include searching and filtering the results. Third, you'd want to update or edit rows of data in any of the tables. Finally, you need a way to delete the data or remove the data. These 4 operations, create, read, update, and delete, are shortened to the acronym CRUD.
All right, so now that we have those basic definitions out of the way for the database part of what we're going to talk about, I'm going to talk about one more thing about sessions. So you use sessions all the time if you use the internet. It's basically the way of the server remembering who you are. So if you were to fill out a survey or if you were to create a survey, someone can walk away and come back and be able to pick up where they left off. Here's a little bit about the sessions.
User authentication, cookie-based server-side sessions. The process begins with a user filling out their username and password and then submitting it to a server, which then validates it, creates a session in the database, then responds with a session ID. The session ID will be saved in the browser's cookie jar, which is a place in the browser to save key value pairs that will be sent back to the server on each subsequent request. It can then respond back with content designed for the currently logged in user. In other words, we have a stateful session between the front-end client and back-end server.
So let's start creating a new app. First, what we're going to do is what we did in the previous video. I'm going to stop the server by pressing Control-C here. And what we're going to do is create a new code directory. So I need to select here. So I can select the whole WebDev folder. And I'm going to create a new folder called Code3. And just as before, we're going to create an app.py. We also want to create a templates folder. Make sure on code 3 and then static for our static content. I'm going to close code 2. A lot of the code is going to be very similar, but I'll start typing from the beginning. That was everything that I have for code 2. And now let's start with the app.py. Before we do that though, what I'm going to do is cd out of this code 2 directory. And I need to install the ORM that we're going to use so that we can interact with the database. And the ORM is called SQL Alchemy. So we're going to pip install SQL Alchemy. Just as the video said, it'll make our interactions with the database a lot easier. SQL Alchemy is installed. We can cd into the code 3 directory for later on when we actually run our app. But let's actually start building our app now. So as before, we're going to say from Flask, import Flask, and we are going to say session, render template, request, redirect, and URL 4. Standard like we have before. What we're going to do here that's new is going to say from Flask SQL Alchemy, import SQL Alchemy. Okay, and we're going to create our app as before, Flask __name _. And now we're going to configure. I'm going to say app.config is going to be an SQL Lite database, colon, and 3 slashes, 1, 2, 3. And the name of our database is going to be survey.db. Inside of the brackets here, we are going to say we want the SQL Alchemy database URI. Okay. The database is configured. We also need to configure our session key. That's why we imported the session function here. Okay, so we're going to say config, and then secret key. And right now, we'll just say a very secret key. Of course, you can change this later on to something that's more secret. All right, as we were saying before, we're going to use classes and objects to represent data in our database tables. So we're going to create a class called response. This is where we will save our survey responses. Okay, we're going to have an ID for each item in the table. It's going to be a DB column here, and it will be an integer, and it will be a primary key. So that's true. One last thing I forgot to put here. We need to also set up the DB. So we're going to say DB equals SQL Alchemy, and we're going to pass it the app. So, next we want to save the question. We want to save the question in the table as well. This is going to be a string of 8 characters, and we want to save the answer. And this is also going to be a string, say 20 characters. Okay, so that is the class that we will use to create objects that we'll insert into the database, data objects into the table. All right, so next we need to set up some routes. We're going to set up a survey route, a complete route, and a results route, similar to the last app. Create the decorator here, app route /survey methods will be get and post. We're not going to create a submit route. This survey will submit to itself. So we're going to say survey and request dot method equals post, 2 equal signs there, equals post. Then you're going to get the answer from the post answer, and then we're going to get the question from the post, say session dot get current question, and then we're going to save the responses, save response to the database. First, we're going to create a new object based on the response using the response class that we just created. Change the question that we got from the form into a string, and the answer. We're going to send those over to the response class that we created. All right. The ID will be created automatically for each item in the table, so we don't need to send that over when we create an object. All right. So now we're going to create a DB session. We're going to add to the database the new response, and now we just need to commit that addition to make it permanent. We're going to increment question or end survey. We're going to say our question is equal to or greater than 5. Return, actually, let's say greater than or equal to 5. We will return redirect URL 4 complete. We'll create that route in a moment. Else, we will session question, and then we will say question +1 and redirect URL 4 survey. Okay, so redirect back to our F. We're getting this as a post request. If we're getting this function is being executed, and the method is a get request, then we are going to just return render template survey.html, and we will create that template later. All right, so that's the survey route. Now we need another decorator for the complete route and also the results. So we're going to create app.route /complete, create a function for that complete function. This is a function that is run when we've gone through all the questions, and we're just going to return thank you for completing a survey. It's done something similar to this before. All right, now we're going to create the results page, the results route. Need a decorator for that as well. App.route /results. Now the function will be results, and you can get responses from the database. Responses from the database. And you get the responses from the database. You get a response query. We'll say response query.all. All right, now we're going to return render template, and we send that to results HTML template, and we're going to send all the responses. Responses will be equal to responses. Okay, all right, so this is basically just getting all the responses that we saved in your database and sending it over to the results template, and it will render the results template. Responses will be sent over to the results template to render. And we saw something like that when we did the results page with JSON. All right, so finally we're going to have a f name equals main underscore, and we want to create the database. We create all. This assumes that the database is created. If it is, it won't do much of anything there. Debug equals true. Okay, and assuming we don't have any errors or typos here or misspellings, that is it for the app. Now we need to create the templates and also our static file before we can run and debug our app. We'll see you in the next one.